Or maybe just a pointer. Yeah. I have some water here. Right? People are very tired, I guess. People are very tired. Too much information.
Probably now, yeah.
I know. I'll be soft.
Okay. So let's.
Okay. So those brave souls that are still standing. So remember where we stopped last time? We did some calculations. We tried to solve the binary spiral problem in the leading order approximation. Those two guys are going around. We did the approximations in which the orbit has circularized by the time that enters the LIGO band, which is, I didn't have the band here, or between like 10 hertz and a kilohertz. So we computed the power by calculating the derivatives of the multiple moment. We calculated the flux just by plugging the three derivatives of this guy. We used the binding energy at leading order. And from these two equations, we were able to solve the change in the frequency in time, which is what is observed here, by mapping the frequency of the orbital motion to the frequency of the gravitational waves up to a factor of 2. And then we saw that the evolution equation had this new mass scale in the problem, which is the so-called chirp mass. Chirp mass. And the name chirp is just because these frequencies you can hear. So it's like it resembles the sound maybe of a chirp. Okay? And by solving this equation in time between two times, like two frequencies and two times, just integrate this equation, this is trivial. We try to see the frequency evolution that you can also see here, how it piles up, and try to estimate what the value of this chirp mass was. So if you solve this equation between 2 points, frequency 1, frequency 2 in this time span, we can estimate here that the wave entered around 35. It went to infinity, so basically it goes into what we call the coalescence time, the time which the frequency goes up, and they merge. Around 43 maybe, so we estimated 0.08 seconds. This will be to the high power, so we can neglect this. We can put 40 hertz here. We can solve for the chip mass. And we estimated also how to get the total mass based on the cutoff frequency by saying that that cutoff frequency occurs when the black holes are almost on top of each other. So there is a typical separation of maybe a few Schwarzschild radius. So from that and the frequency that you can solve from here, you can try to solve, if you plug R to be close to the Schwarzschild radius, you can solve for M if you know the cutoff frequency. And then we got some masses of around 30-something, 40, 30, which is very close to the actual values, which are 36 and 29 plus minus some error. So what I want to do today is keep on going and trying to analyzing the data and how we're going to keep on improving on the estimates of this type of equations, solving Einstein's gravity to higher orders in this perturbative approach, which is called the post-Newtonian expansion, which we'll see will be needed not only for the extraction of the parameters, to be able to identify the correct sources, and to learn about the structure of the bodies that produce the signal. So one more thing that I didn't have time to do last time, that we can estimate also by looking at this picture, is the distance. So here I was basically playing with the frequency evolution, but there is an amplitude. And we can solve for the amplitude. If you remember, that was the two derivatives. So the radiated field, H, will scale like 1 over the distance times the second derivative of the multiple. So there will be some angular dependence. And here, let's say I look at the plus polarization. Remember, it was H plus minus H plus that we studied at the beginning. So we can just look at the H plus and have an idea of how far this source was by just looking at the amplitude that we observe. And if you go ahead and try to solve for the amplitude, you get this equation. I'm just plugging into the expression for the second derivative of the quadrupole moment. And this depends on the reduced mass. It depends on the frequency. It depends on R, just from here. and it goes 1 upon the distance, okay? So if you transform this, I'll stop using carrying the c's. So I use c equal 1 units from now on, unless otherwise noted. Then you translate this into frequencies. I forgot to put the cosine. So just look at the amplitude. So we know how to relate this as omega, right? So there is a time dependence, but the amplitude, which is what we care, is this. And then we can solve from here for a given frequency, distance, and amplitude, how far the source was, okay? And then you get an equation like this that relates, given a shear mass, and given the frequency, we get the maximum amplitude. What is the distance to that source? And just plug in some number, you get about 100 megaparsec. The cutoff frequency is more like 300. The shear mass is a little higher, it's 30. So you get around 500 megaparsec. This is the equation, but if you plug in the numbers, you get around 500 megaparsecs, which is, 1 parsec is 3 light years, right? So it's about 1 point something billion years in distance, right? Which is more or less, this was 400 megaparsecs away, that you can easily also estimate from here. So that's one of the unknowns in your theory as well. One of the parameters that you want to extract is how far the source was. That you can get from the amplitude and the frequency, given that you extracted already the shear mass from the phase evolution, okay? Another quick way to get the same value will be going back to when we computed the power. So this will be directly from the amplitude, which has the 2 derivatives of the quadrupole. You can go back to the power calculation that we did, that if you remember, there was the pseudo-stress energy tensor that we integrated. So you have a Poynting vector type calculation, and then you say, okay, there was an amplitude, there was a derivative of the amplitude that came from the pseudo-tensor, it was an integral over the sphere, so basically the power scales like this. And the calculation that we did over here, that actually, for the binary system, we found that it scales like this parameter, that is v squared, that we call x, and it's the perturbative expansion parameter that we're going to have in our theory, is x to the 5, roughly. This will be a quarter, so this will be an order 1 number. Remember that nu is less or equal than a quarter. And the quarter is a symmetric mass ratio. The quarter occurs for equal masses. So this roughly x to the 5 is the power in terms of the Planck luminosity that I told you was around 10 to the 52 watts. So we can estimate that the merger or the cutoff frequency maybe is the innermost stable circular orbit or a little bit farther. So this is just ballpark. To get an estimate similar to this, you can say that x is about 0.5 maybe when the skies merge. It's a little less, but rough estimate. And then you can get, again, an equation like this. It also tells you that there is a lot of power. So if this is like 10 to the minus 3, 10 to the minus 4 of 10 to the 52 compared to the sun, which is 10 to the 24, and 10 to the 26 stars. This is a very luminous event. And from here, if you put the cutoff frequency that we have, there was about 300 hertz, you get about the same distance, okay? So these are the parameters of the source that we're trying to extract. The masses are very high, so we don't think these are neutron stars. We think these are black holes. And we can extract the masses, the M1s and M2. I haven't told you how to get that, and this is what we're going to walk into. I tried to estimate the M1 and M2 from the cutoff frequency, but in fact, the way it's going to be done is by including corrections to this expression and trying to model the wave with the waveform as accurately as possible. And this will be our leitmotif, try to understand what the sources are. Now, something very interesting that you can see from here, this is just a rough estimation of the parameters, right? So we're going to try to do this more systematically. One interesting question that you might ask is like, okay, if these are neutron stars, are they actually black holes? If they're not neutron stars because they are too heavy, we know that the mass of a neutron star is bounded about 3 solar masses, and this is very high. So we think these are black holes, but how do we know they are black holes? How do we know for sure that we saw black holes? Well, one very strong indication that they are black holes is that the cutoff frequency that we get, which is around 300 hertz, and the total mass that we extracted, I use this expression to solve for M. But we will see that we're going to get the total mass differently by including the corrections to this expression that will break the degeneracy. So if you do more accurate determination of the parameters through including post-Newtonian corrections, you will be able to get the mass M1 and M2, and then you can go here. With the knowledge of M1 and M2, you get the total mass. You know the cutoff frequency that you can get from here, and then you can try to solve what is the distance at which the waves shut off. And it turns out that the distance is very close to what the Schwarzschild radius would be of something which is about 30 solar mass object. So it's extremely compact. So there is out there a very extremely compact object in nature of about, so this is the shear mass, but remember we determined M1 and M2 around 40 and 30. So let's say 35, it's actually 36 and 29 what came out of LIGO. So of over 30 solar masses object, extremely compact in nature, which is not a neutron star. And when we do the waveform, and we solve, for example, in Einstein gravity, we see that the numerical GR waveform exactly reproduces what we observe, so then that gives us even more confidence that what we saw were black holes in Einstein gravity. But can we really tell? Can you really, well, in this case, we're including the entire waveform, so if there was something else, you could have seen maybe here departures, but you need very accurate waveforms to be able to tell whether this was truly a black hole or not. So this will be our goal. Ultimately, yes, this seems a very strong indication that the numerical waveforms of black holes in Einstein gravity fit the data extremely well. This estimate that I just told you suggests it's a very, very compact objects, which are much heavier than neutron stars, so they are not neutron stars. The density is 6 orders of magnitude bigger than a white dwarf. You can just estimate the density by thinking about putting all this mass in the region that you can fit up to the cutoff frequency, and you'll see that it's even 6 orders of magnitude bigger than a white dwarf. So then what is it? What is it that we're seeing? So that's the goal. And how we're going to do this is by doing this whole business that I just described more precisely. Okay? So that's the goal. The goal is to try to construct templates, which are a little bit more accurate than what I just did, and try to match the data with the templates, basically trying to see the waveforms in the middle of the noise and the data, whether this is a template, it's something you construct analytically, this is the data, you try to see if they match. So before I go into this picture, let me ask if there is any question about this very simple math. It takes a little while to sink. This is high school physics, right? And we're learning about the most amazing objects in nature. So it's really incredible that we can look at that picture and almost conclusively say that there are very heavy objects in nature which are extremely compact that resemble black holes of Einstein gravity producing gravitational waves the way that the theory predicts, right? But we want to give a little, yes? Maybe we can go that later, yes. Let's do calculations first. Okay, so now let's go to this picture, and I'm going to tell you a little bit about the way we're going to do this and how. So tomorrow, hopefully, I will go a little more advanced about these new modern approaches that we have developed to compute the phase evolution and the amplitude and so on to high precision. I will see why we need this and how this method has allowed us to push different tiers of analytic understanding to the state of the art today. And I was trying to convince you at the beginning, we still need to go a few orders more in this parameter x to be able to tell for sure what is the nature of these objects, because of effects like tidal deformability and so on, which start to play a role at high orders. Okay, very good. So now, as a theorist, what you need to do is to construct the waveforms. So basically, what is in a waveform? This is the detection of the lower mass case, about 10 solar masses, binary black hole. So since the mass was lower, it lasted longer in the detector. So we have a longer in spiral. And what I'm going to concentrate the most in trying to reproduce what the waveform looks like and try to match it with observation is what we call the inspiral phase, in which we can use this post-Newtonian expansion, in which we're going to go beyond this calculation order by order and this x parameter that I just erased. That is going to be our expansion parameter. So we're going to try to solve the binary inspiral problem. And there is some radiation for objects which are compact in an expansion in V. V over C is going to be less than 1. You will see when tomorrow, hopefully, maybe later today if I have time, or in the discussion, why ultimately there are many ratios I can take of expansion parameters here. They all are related to powers of V. So everything is going to come out with powers of V. But it's going to be mixed up. There's going to be interactions of different regions. Modes that live here, coupled to modes that live here, to modes that live here. But because the ratio of all those scales comes out order V, then the expansion parameter will be V. But your role, especially in the approach that we develop, which is an effective zero approach, will be to disentangle the relevant physics of different scales to be able to do independent calculations and then put all that together at each order in the post-Newtonian expansion. Okay? So that's going to be our goal. So I'm going to concentrate mostly in this inspiral phase, which is the phase in which I can calculate. In the case in which now those guys get very close to each other, there is the merger part, and then there is the ring down, in which you can also do perturbation theory, and you have the quasi-normal modes. In the numerical regime, these velocities are large, right? The potentials are large too, so this is comparable to Gm over R. If I put the C, I should put the C. So it's comparable to the binding energy. And if this is getting large, also the nonlinearities of GR are going to be important. We will incorporate those perturbatively, but at some point it's non-perturbative anymore. And then you have to rely on numerical codes. Unfortunately, or fortunately for us, numerical codes cannot cover the entirety of cycles, and we will see how many cycles we need to model. This will be part of the story. How well we need to model the waveforms to be able to tell, well, first, that we had a detection, second, accurately the parameters, and third, to go even beyond and try to learn and distinguish the nature of the objects, okay? So numerical waveforms can last for this long, but they will take many months to run, and then you have to move the parameters, like the masses and the spins, to construct a template bank, and that will take a long time as well. So that's why analytics, also because if you have analytics, you can actually do the calculation. You have waveforms that you can now use for your data analysis. So some effort has been going into trying to construct an analytic description that matches the entire number of cycles, that also matches into the numerical waveforms. This is called effective one-body approach, for example, which attempt to match analytically the entire waveforms. Or there are more phenomenological approaches in which you just try to fit the post-Newtonian into the merger and into the ring down, which, as I said, this can be also done perturbatively by studying the ringing of isolated black holes. So after black hole forms, it will be a Kerr black hole because most of the angular momentum is going to go into the spin of the black hole, and it's going to ring, and that ringing will be here, and you will try to match it. Now, the errors are going to be large. This might be difficult to see. We haven't seen more than maybe one mode. I'm not going to get into this. I'm going to talk about the one that has the most cycles, which is the post-Newtonian expansion. And this is a template band with different spin parameters, and then you see how we did the matching, which is try to get from the data the waveform. Okay? So let me now walk you into how this is going to work. And this will be our task for the remaining of the course. But first, let me just give you a very brief flavor of this, the part associated with the data analysis, and also with the amplitude. This I can do a hand that I haven't told you much about yet. This, how does it look like when you look at these amplitudes? I will get to here in a second. How does the wave looks like in the LIGO band? How does the amplitude scale? And then you will see here those numbers. You will understand a little bit better what these graphs mean, not just in frequency, but also in amplitude. Okay? Very good. So the idea is that we're going to construct waveforms, and I'm going to concentrate in the post-Newtonian part, but as I was saying, we have to stitch together all these regimes of the binary problem. And you think that there is, in this noise, some signal in nature. So the point, this is a waveform. The theory. So you have some bias about what is in there. And there is some signal on top of the noise that came from nature. This is the signal, this is the noise, this is the gravitational wave emitted by some source that you will try to describe. And the noise has some spectral function. This is what we saw when we see these plots about the buckets of LIGO and so on. They're basically giving you a representation of the noise. That for historical reasons, the power spectrum has this factor of a half. So there is some noise. There is some waveform that tries to match the amplitude. And okay, there's a whole theory about how this is done. I'm just going to give you a brief flavor so you have an idea how this is done. And when we estimate the parameters, how this is going to play an important role in terms of what we call the signal-to-noise ratio, right? How much you trust that you saw something and how well can you extract the parameters depending on how long your waveforms are. Because naively you'll think that the number of cycles, 1 over the number of cycles will give you a rough idea of the error that you're making in the extraction of the parameters, provided that your waveform matches the signals well. And since you have many, many, many cycles, you want those two to be very highly correlated, not to be out of phase, otherwise you're going to miss the signal. Okay, so that's going to be also very important, that this guy and this guy, that this guy approaches this guy as good as possible. Okay? Because there are many, many, many cycles that you're going to observe. And this is very important because over the time span and all the cycles that the system is going to be in band, you want this to correlate with the signal as much as possible. So what people do is define some inner product in the space of possible waveforms. It's defined like this. So this is just to simplify the way, this is trivial. It's just the notation simplifies significantly. Instead of doing integrals, I just write this. And this factor here, that's complex conjugate. So how this is done is a little bit more elaborate. You have a filter. You're going to filter out in your detector the frequencies. As I was telling you in the first lecture, you're going to factor out the frequencies in which you have a lot of noise. Like a low frequency, for example, you put a wall, and you can model this such that it's infinity for frequencies below 10 hertz, in which you know that the time variations in the seismic, what you call the seismic wall, seismic variations in the gravitational potential, at low frequencies, it's like a static in some respect, are going to dominate. They are much, much bigger than the amplitude of the gravitational wave that you try to detect. Okay, so you filter that out by putting this guy here. And this is the power. I mean, there is the optimal filter. Let's not go there. Let's just trust me that this is a way in which you can quantify the presence of the noise in the correlation. So you factor out, you filter out the part where the noise might dominate, okay? Very good. So then we define the signal-to-noise ratio. This is just to give you a flavor of how this works before we actually do the calculations. So you have to get something that is above the threshold of the noise, so you have some confidence that you detected something, and that's what this LIGO band is. Okay? So you're going to define the signal-to-noise ratio, which sometimes is called rho, as a correlation of the waveform that you have with the signal that you want to pick up this part over the root mean square of whether this is correlated with the noise, right? Normalized by the noise. And this is the product that you use. It's just the way it's written. So you will see these expressions in LIGO papers. You will not see it like this. What you're going to see, which comes from here, what you're going to see is that then you average over all possible realizations of the noise, and this looks a lot like an inner product in quantum mechanics. You sum over the basis. So once you sum over the realizations of the noise, this is essentially this guy, the 1/2. And here you want to pick up the correlation with the signal, not with the noise, with the actual amplitude that is hidden in the signal on top of the noise, right there. So a typical estimate, you want this to maximize the distance between the waveform and this guy. So a natural estimate, once you construct the waveforms, of what the signal-to-noise ratio will be, given the bias, and that you know what theory produced the signal, is roughly this. And this is what you will see in all the papers. You will not see much of this derivation unless you do a little bit more of the data analysis and so on. But what you will see in LIGO papers and et cetera, you will see something like rho square as your signal-to-noise ratio, defined like this quantity. So you see the integral of the waveform in frequency over, so it's a half, it's a 2, you get a 4 over the signal f. So I could have just written this and told you this is what we do, but this is like a very short motivation of where this comes from, okay? So this is our signal-to-noise ratio. We want to maximize this quantity within some bucket given by the detector. So filter by the detector, we want to correlate the signal as well as possible. Now, you will see what is plotted is often something else. Just for convenience, there's a few redefinitions that we can do. Also, on dimensional analysis is convenient because we're going to Fourier transform. This is h in frequency. So you see where we're going, right? I computed a second ago the amplitude from which I got the distance in time. Now I'm going to Fourier transform that and put it here with some model of the signal-to-noise of the spectral function to get my signal-to-noise, and use this to extract parameters as good as possible, okay? That's what data analysis works. You will see a Fisher matrix eventually, and if you've done any of this in cosmology, you'll see that it's exactly the same, okay? But there is some convenient ways to parameterize this, and because the amplitude is true, the amplitude is dimensionless, but you Fourier transform, so you put in units there. So sometimes it's useful to define, this is not cutoff, this is just a notation that will show up soon. Let me just put this in here then. There is this amplitude that is defined, h twiddle is the Fourier transform. I'm using hat here for the waveform. So now let's abuse notation. I'm going to take away the hat. I'm going to just talk about the waveforms. And I'm going to say this is the Fourier transform in frequency of the waveform. And that's why the notation in there that I just copied from papers that people write that. So once you see it in a paper, now you know where it's coming from. So there is a definition, which is that one over there, that picks the 4. And you'll see why I put an f squared here. This is going to be motivated by physics. But also because now you get rid of the units. So you get something which is dimensionless. And you're going to define some amplitude of the noise, similarly to what you did there, to reabsorb this factor here. Where is what? The hat was the waveform. H was the signal. Now I said this is approximated by the waveform, provided that you have this bias about the best, the closest, that you're going to try to minimize the distance between the waveform and the signal. Therefore, this will be approximated by this, in which I replace this guy by this guy. So this is something I can compute now analytically. Now, this is my waveform. When I came here, I should have put here the waveform, but to avoid cluttering notation, I removed the hat, and I put the twiddle to emphasize that I'm in Fourier space, because at some point, I have to do all the calculations that I did in time in Fourier space. And when I do the Fourier transform, you'll see extra terms popping up, and that's why I have to be very careful in telling you that I'm in Fourier space. In fact, I'm even going to put f tilde at some point. And this is going to be pedantic, but needed, because we have a function of time, which is the frequency changing in time, that then we need to Fourier transform. And because the frequency is changing with time, it's not a delta function. When you Fourier transform, there are going to be corrections, and then you have to distinguish the function of time, which is the orbital frequency, from the Fourier transform variable. Okay? And that's why I'm pedantic about this twiddles. So again? I cannot understand what you say. Well, this is what you need to compute. You have here the signal that you're going to get in your detector, and you have to compute this. Now I'm estimating what would be the signal-to-noise ratio, provided that I do this in a way which minimizes the distance between the waveform and the actual signal. Once I do that, I know that these two are going to be correlated, and therefore this calculation here, which is data and waveform, is of the order of replacing data by waveform, because that's the closest that the waveform will be. In some sense, you have data and you try to project data and get as close as you can of the space of waveforms. So this distance is small. So it's true that you have to do the inner product with the actual data. You're going to do a waveform that tries to approach the data. This distance is the smallest you can get, projected in the space of data, and therefore this product is similar, comparable to this product. And this I can compute, because now, after I do this, after I get the best waveform that fits the data, I know that the signal-to-noise ratio is roughly the same. If I compute this or if I compute this. Now I go to Fourier space, do this integral. Now I do this redefinition. Why? Well, because this guy has units and I don't like units, so that's what I multiply by f. And we will see that this also carries information about not only the amplitude matters for the data analysis, the number of cycles that you spend at a given frequency will be key. And that this f is going to play a role in that. And the other thing is that we like logarithmic plots. And that's why we redefine this amplitude. Okay? Unfortunately, you see all this digested at the end of the day in all these LIGO papers, but it's very simple. Right? Okay, so after these redefinitions, I get the following. I get if I get plots of logs, which is what you see all the time is logarithmic plots, right? Then the signal-to-noise ratio is the relationship of those two guys. This gives you the extra f that you pair with this guy to kill the f squared. The 4 survives and stays here. Okay? So this is our signal-to-noise ratio. And then you see very simply that when you see plots like this, or plots like this, about there is an amplitude, and this is the guy that they're going to plot. They're going to plot something which is dimensionless, but in frequency space, so they're going to plot this hc on the vertical axis between, say, strain, hc, between 10 to the minus 21 and 10 to the minus 23, say, which is more or less what LIGO is sensitive to. And there is some noise, which will be the plot of this guy, that will be your bucket. And then you look at the plot, for example, the red, and the area under that plot within 2 frequencies within the LIGO band will give you the signal-to-noise ratio. So then you can just look at the plot and understand what's going on. This is the key equation, okay? And these are, for example, the 3 events observed at the time that the LIGO finished the O1. And there was the longest that I just told you. There was the first detection, there was the shortest, the one in blue, even though it's in red up there. And there was this other one in green that was, as you see, the signal-to-noise ratio was not that high for them to be confident for 2 reasons. One, it's lower, as you see, but also it enters there a little lower as well, where there's a lot of noise, which gets a little better higher up. So that's why the green one was not confident enough for them to claim a detection, okay? So what I'm going to do now is motivate a little this and calculate in frequency space what the waveform looks like after the calculations that we did before. These are the leading order results that I'm going to reproduce for you now. And then we're going to do dot, 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 and start including the corrections and seeing how those corrections will be used in the data analysis to extract the parameters of the source. Okay? Is there any question? Let's save them for later so we have something to discuss about. Okay, let me do something. Let me motivate. Okay, let me do this first and then I motivate. Okay. So the plots that you see, as you see, so you should ask immediately, it bothered me a lot when I saw these plots that they're going down. Okay, the amplitude is going down. Except at the very end when you say that ni, the amplitude is going down. But that's not what you expect, right? These guys are getting closer to each other, orbiting quite fast. You think the phase is going faster, right? The phase, you see the wave piling up, the frequency, going up. But the amplitude is also going up. So how come I'm plotting something that goes down? Because you're not plotting the energy, you're plotting this value, this F. And as you see there, this is not yet the HC. This is just the H Fourier transform in the case with frequency, after you do the Fourier transform and so on. So you are not plotting, and then you multiply by F squared, and it's still the case. It goes like minus 1/6. So that's what you see, it goes kind of like this. So after you realize that what is plotted is not what you will have expected, then you're happy. But it should bother you when you see that picture. You should try to ask, what the heck are they plotting? Right? Okay. So now we're going to do the Fourier transform, and we're going to try to get those values here from the calculation I just did for you last time. Okay? And we need better chalk. Okay. Let me remind myself where I am. Very good. So let's say you have, so we have the waveform. Let's just concentrate. There's some angular part that I'm not going to look much into it. So we have an amplitude, and we have a phase. So this is, there in that Q parameter there is some angular dependence and the polarization and so on. Let's not go there. So here we have an amplitude, and we have a phase, which is the integral of the frequency. And we saw for this, like a second ago. I just rewrote this for you. We got the distance from this guy, and we got an equation from the frequency, from the power, that we also got here. This was the omega t, or 2 omega t that we had in there. In the case of a constant frequency, this will be, at every time the frequency is constant, but the frequency is changing with time, so this is a function of time in general, because we computed omega dot over omega squared, which is very small, but still is not 0. So that's why the phase is actually an integral of the frequency. And the amplitude we got from the quadrupole formula, the Q double dot, and so on. And that's what I'm trying to do, is reproduce this at leading order, okay? So now the key, this is our function of t. I'm going to drop these hats now. And I'm going to do the Fourier transform, which is, as you know, just this. And because of what I was telling before about the units, this is dimensionless, but we have Fourier transform, now we pick in units. That's also one of the motivations to do that, to get rid of the units. Okay, so this we can write as A0 e to the I5. Okay, so now what we're going to use is the approximation in which the phase is varying slowly. And the amplitude also changes very little compared to the frequency. Then you can expand the phase. The second order, you do this saddle point approximation, and then you can compute this. So this is equal. The the stationary phase approximation, if you want, because there's a very, very adiabatic change of the frequency, and the amplitude remains mostly constant in a period. Therefore, we can approximate this. And let me just give you the answer. So the time as a function of the frequency, and crucially, we pick this factor of f dot. This is the frequency. This is this function. Now you see why I'm pedantic. This is the function of time that comes out from the evolution that I was solving before. This is my f twiddle, right? So this is the function of time, and I'm going to find the time. I'm going to tell you who this guy is as a function of f twiddle. And then I get the phase, e to the 2 pi, t of f twiddle, minus, now comes the phase, and there's a square root of I that you get from when you span, because there's an I. And then you get the two derivatives. So what you do, you span this phi dot, phi double dot, and the square root of phi double dot is the phi dot. And there's a square root of I, that is just the pi over 4. Actually, I forgot the 2. Okay? And who this guy is, who t of f is, well, we have the functions of time, the frequency, which is the derivative of the phase, and therefore, as we have expected, you find the time by solving equal phi dt. So you solve for the t as a function of f tilde by essentially solving the equation that you would expect to solve for, equal to the frequency. So this is 2 pi f, but f as a function of t. So you have to solve for t as a function of f, you plug it here, and that's how you get the phase. That's just doing the Fourier transform, but because you have a natural frequency in the problem, which is the orbital frequency, is that those two get mixed up, and you have to solve. And why we can do this? Because we can track time with frequency, because the frequency is changing with time. So that's key. If the frequency was not changing with time, we have delta functions. We cannot use a frequency to track time, right? But then we are also in Fourier space. That has nothing to do with that. We're just looking at the Fourier space because that's the spectra that we have for the noise. Because often we understand better the Fourier modes of the detector, okay? Very good. So now we just have to go on and calculate who those guys are from what we had before. And lo and behold, you're going to get these expressions, and I'll show you in a second. But from here, I want to tell you why this definition, and essentially why motivates this definition is because what you have is that HC now, when you Fourier transform, you pick up this factor of f dot. So essentially, this gets something like this. S squared over f dot times H0 in Fourier space. Because this is the amplitude Fourier space picks up this. So it's not just H0, it's H0 over phi dot, square root of phi dot, and we multiply by f squared. Okay? And now if you think about the phase as a function of the frequency, and the frequency is keeping track of time, so the phase, if you divide by 2 pi, you essentially get the number of cycles. So the phase is a function of time, it's a function of frequency. When you move in the band of the detector, gives you an idea of the number of cycles. Around a given band, I can say I do Taylor. So around some given value of the phase around some given frequency, I can estimate the number of cycles at that frequency by saying, oh, within some frequency f and f I can put delta f, but I can normalize it to like where you start in the LIGO band. And who's this guy? Is d phi df, but I can do d phi dt, df dt. And d phi dt is f, and df dt is f dot. So this is going to give you number of cycles. So that tells you that the hc is roughly the square root of the number of cycles times the amplitude. So not only the amplitude matters, the number of cycles as well in determining the signal to noise ratio. And this is going to be key why the analytics of the inspiral phase contribute a lot to the signal to noise ratio and to the accuracy of the estimates, even though much of the amplitude comes from the end. So even though the amplitude is dominated by the end, and you'll think that's what will dominate the signal to noise ratio, that's not true. That's not true, A, because at the end, you might be hitting the band in which you have a lot of noise, right? In fact, for neutron stars, the merger might even occur outside the band. So you don't even get to see the band. It's completely damped by the noise for neutron stars binaries. So it will depend on the mass whether you start merging in a region in which this is very large, even though the amplitude part is going up. But also the number of cycles are going to be important because early on, you're going to go around, I erased it. I'll tell you who this function is. It goes like 1 over f to a high power. So the lower the frequency, the more cycles, the more contribution to the signal to noise. So it's a game. And the analytic side will contribute a lot, especially for low mass, because the lower the mass, the more cycles in band, the more the analytic of the inspiral will matter. Okay? Not only because the numerics cannot do it, it's because it will contribute significantly to the signal to noise ratio. In fact, okay, let me skip this. You can actually do the integral. Maybe if I have time at the end, I'll show you. Because you can model this bucket with some power law, flat power law, and just go ahead and do the integral and estimate where the signal to noise ratio peaks. It actually peaks between 40 and 100 hertz, which I wrote it down there. Okay? And this you see why the detectors are important, because then you see how LIGO is improving and how this is going to get better and better and better. Okay? So now let's just derive these formulas down here, which are the ones that enter in this calculation. And then you'll see at the end how this calculation is used to estimate parameters. And then we're going to embark in doing this more accurately tomorrow with the tools to solve for the problem of motion gravity. Very good. So let me just quickly derive this for you. I'm trying to be as self-contained as possible in telling you what the story is. I haven't done any complicated mathematics yet. I'm going to pile all that up for tomorrow. But at least you get some message, right? Very good. So I had an expression that I used to extract the distance. There is some angular dependence I'm not going to care about from the amplitude. Say you look at the plus polarization. We had an expression that I wrote for you. I'm not going to carry the C's anymore. In the case with 1 over d. And I used it to estimate the distance. M chirp. This is the chirp mass. Frequency to the 2/3. Cosine of phi of t. And this guy, the integral of 2 pi f dt. So the equation for the change I erased, I had it here. The change of frequency with time was the equation that I had here. We go from this expression to this expression. By using the most important formula in this course. Solving the two-body problem in gravity, 2 observations. So you get an equation that looks like this. Here, F by Z. And motivating what's going to come next, I'm going to tell you that ultimately, when we include the corrections, this is the linear order. Expression that we got. I know that I repeat a lot, but this is how we learn, by repetition. We got from getting this, from knowing the flux and knowing the binding energy as a function of omega in the adiabatic approximation. So by including higher order corrections to these expressions, we're going to correct this. And the corrections are going to scale with this x parameter that we defined before. I already defined it, but for it again. That goes like V over C squared. Well, not C's anymore. So that's our expansion parameter. And they're going to be corrections that also scale with the mass ratio. This is symmetric mass ratio. And I'm doing this because there is an expansion parameter in X, but there is also an expansion parameter in nu. You could study the limit in which one of the guys is much, much heavier than the other guy. And that's called the self-force program. And you can try to fill up some of these numbers by doing calculations in nu. Some of these results are known up to nu squared, to all orders in X. And the results that I'm going to show tomorrow are known at 2x to the 4. Not all of them. We still don't know this 2x to the 4, but partially we know this guy 2x to the 4. And you'll see that it's analytic in nu. It will come out up to nu to the 4. There are no higher powers on nu. So there will be a marriage between how many nus you get here and how many x's you get here. So this is going to be like this. There's going to be a correction. There is something here which is really pretty, which is completely unknown to electrodynamics. It's really a gravitational effect. It's called tail effect, which has to do with the different expansion parameters that I was telling you. I will tell you where this guy comes from tomorrow. And it's the interaction of the emission of the gravitational wave with the binding energy of the system that gravitates. So it gives you a Coulomb force that basically changes the power. So diagrammatically, remember that we have the multiple emitting. So this guy has a monopole. The monopole, let's do like as if it's moving in time. It's not really propagating, it's a source. But let's say as if it's moving in time, it's a diagram like this. So there is no propagator here. It's just two insertion of sources. Monopole coupled to quadrupole through nonlinearities. In the emission, when we compute the 1-point function, we had to include interactions like this. Monopole, quadrupole interactions. That's called the tail effect, and it's universal. And it's very nice. It has beautiful physics because it leads to the renormalization. This means that this guy is going to run, and also this guy is going to run. So it's as good a field theory as you can get. And it's completely classical. Okay, why? Because you're going to run into divergences that you're going to have to renormalize. Not only UV divergences, you're going to run into IR divergences. These factors of 4 pi come from IR divergences. So there's a beautiful field theory story here. And if I have time tomorrow, I'll tell you what you do with those infrared divergences because they pollute the entire calculation. And it gets very, very interesting when you have to deal with UV and IR divergences at the same time. And when we hit the x to the 4, this was one of the obstacles that led to the more traditional methods to introduce a series of ambiguities because they didn't know how to deal with these divergences. We show how to do it, and then we solve this issue of ambiguities in a very neat field theory way. So if I have time tomorrow, I'll tell you about it. Okay? So these are these effects that basically will provide the absolutely classical effect of RG flows, which I know you can understand RG flows in many different ways. For me, perturbatively, it's just because there is a bunch of logarithms. So we will see logarithms popping up. And for a field theorist, you see logarithms, you can sum them. And that's what the RG flow will do for you, okay? Very good. So these are dot, dot, dot. So now, we have a change in frequency in time. This is the Newtonian plus quadrupole formula, and we'll see how to compute these effects. From here, we're going to get the functions that I was trying to get for the Fourier transform that I'm going to use in the data analysis. So we get this phi of f, which is the one that I had here. Did I erase it? The phi as a function of t. So let me write t first then. You can solve for t of f. So you have a reference time. Often we take the collision, the coalescence time, the cutoff when the wave stops. Remember, these t's are going to pop up because remember, we also look at the solution in time. So there's going to be some initial condition and some binary condition. The wave enters somewhere, and it lasts until somewhere. So there is a phase that you're going to have to match at some point, like the end point, this is the coalescence time, where the frequency is infinity that we use to extract the shear mass. So those parameters you also need to solve from the data, and they're going to enter everywhere, okay? But it's a reference time. You can choose anything. And so here is the solution for the time. The shear mass by f m chirp the minus ether. I'm not doing anything. I just solved this equation a second ago. I'm just rewriting it, right? The two times, the two frequencies, and so now I'm using just a reference. If I rewrite this as f1 and f2, and t1 minus t2 is what you get. The difference here is that I drop, by choosing the coalescence time, the 1 over f to infinity is 0, so it's not here, okay? But there's no mystery. There is no mystery. And this is the same equation that I also solved, but now it's for the phase, which is the integral of that function, and then you plug this in here that allows you to track time with the frequency. F m chirp to the minus 5 there. Okay? And this also dot, 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 right? This is 1 plus dot, 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 1 plus dot, dot, dot. The whole point of precision gravity is dot, 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 dot. Okay? So very good. Now I go on and do the Fourier transform that I just told you how to do. And I get an expression for the, I was going to write down, but it's there. This f now is the f twiddle. Okay? Because that's the t that I solve. Remember, I need to solve the t. What did I write? The t at which the phi dot of t is equal to 2 pi f twiddle. So you solve for t of f, and that is now f twiddle, and you plug it back, and then you get the amplitude. The phase is that thing that I wrote before. And then you see the phase f phi that I needed is down there. And then there's the 2 pi, and this is the reference part, and this is the square root of I. Okay? So very good. So there is also an amplitude that I didn't write, this q, that depends on the angles. And well, the shear mass is factored out. There is the m to the phi 6. But the corrections here are going to depend on, they're going to break the degeneracy. They're going to depend, for example, in the mass ratio. So it's true, I didn't know that I can only extract the shear mass. But if I include these corrections, I start to see the dependence on the masses. And here, they're going to have dependent on the spin that I haven't told you anything about. The spins are going to also correct this expression. They will also enter, and you need to break the degeneracy of the spin because they're going to be combinations of S1 and S2 and projections of the angular momentum. And those are crucial for formation of the systems, formation mechanisms. And here, at some point, you're going to have an x to the phi that knows about these tidal effects. And this is how we're going to tell if this was a black hole or something else, because for black holes, lambda is 0. And I'll tell you a little bit more about this tomorrow. So it's a beautiful test of GR that you can really nail whether this was a black hole or not, because you could still, with the data that we have right now, you could still match everything with a very compact object which is not exactly a black hole. How are you going to tell? Well, when you start seeing properties that distinguish the black hole from another object. A black hole has a 0, else like a boson star has not 0. Or black hole hair, like condensates of ultralight particles, will also give you a tidal effect which is not 0. So that's the goal. Okay? So how much time I have?
0.
Okay. So let me just say minus 2 things and conclude for today. Which is the following. So this is what I'm trying to tell you. All these corrections need to be computed, and I'm trying to tell you why they're needed to extract parameters, and also the faithfulness of the template to see whether you are reproducing GR, to get the spin parameters, to get the deformability, but also for that analysis they're crucial. Because if you compute now the number of cycles, I have the phase. So now I know what the phase is, I know how many cycles you have between frequency 1 and frequency 2. You can estimate, given different post-Newtonian orders, corrections will change the expression for the phase and therefore the number of cycles that you get. And you'll see that up to x to the 6, which is this 3pn, that includes all these tails and corrections to the tails and so on, you'll see that it's roughly of the order of 1 or 2 cycles for different masses within the LIGO band. So this means that even though this is needed for data analysis, this is needed for extraction of parameter and so on, to really also say and claim that you saw the signal, if you do this inner product that I was telling you at the beginning, between the signal and the waveform, and you're off by a cycle, then you're going to have a mismatch that could be significant. Well, it depends on how many cycles you have, right? But if you start getting off, and you're off by a cycle, then this could be a large mismatch, and you might miss the signal. If the signal has a very large signal-to-noise ratio, then it's okay, because then this is not very suppressed down here. Maybe it's okay what you miss up here. But it's very important that you track the signal very well. And that means computing what I told you, the energy and the flux to high order. Here's the corrections that I put ... For example, the first order corrections. That my plan was compute this. But first I need to define the theory, so we'll see how much we get done tomorrow. But this already, you see, breaks the degeneracy. That's the nu as mu over m. That breaks the degeneracy of the first term that only has the shear mass. Okay, and that's the tail, the 4 pi term that I was telling you. So that would be the game from now on. Okay, thank you.